Ừ. All right, it's 8:30. Let's go and get started. All right, good morning, everyone. How's everyone doing today? All right, hanging in there. End of week 12 now, right? So yeah, so we're I know it's hard. It's this part of the semester is a grind, but I appreciate you guys being here, and I appreciate as always, I appreciate the effort you guys are putting into the class. So thank you guys. Okay, so the plan for today is we're still in Fourier, but we're on kind of the second part of Fourier now. So we're on Fourier transforms. So we talked about it a little bit on Tuesday. So I think we did it for about 30 minutes then. And so we're going to continue on today. We'll see how much we finish. I'm hoping we can kind of finish everything with Fourier today and kind of wrap that up. But if not, we'll finish it up on. Okay, so I also just wanted to repeat the announcements that I said on Tuesday. And so remember the due date for homework 5 that we do this Friday, tomorrow. To make sure you guys are working on that. So homework 5 is all about Fourier series. And so we finished up everything you need to know about that on Tuesday. Homework 6 is going to be a short assignment. And so that's going to be on Fourier transform stuff. And so the stuff that we covered in the second half of Tuesday as well as today. So homework 6 is going to be due next Friday. And then our second midterm, I pushed it back a week just so that you guys have more time to study. And so that's going to be Thursday, April 27th. So 2 weeks from today. Okay. So I think originally in the syllabus, the second midterm is supposed to be next Thursday, April 20th. But we're a little bit behind, and I want to give you guys a bit more time to study relative to the first midterm. Also, 420 is becoming a holiday now, so you guys can enjoy that too. And so I pushed the second midterm back a week. Okay, and so we'll do the second midterm. We're probably going to start new stuff before the second midterm, but the cutoff in terms of content for the second midterm will be 40. Okay. And so just like last midterm, next week I'll put out a study guide for the midterm. I'll put out a practice exam next week too. So that's one thing that you guys gave me feedback on kind of the break surveys. And so I'll put out a study guide, I'll put out a practice midterm, and then next Friday I'll film a review video. So just like I did for the first midterm as well. Okay. Okay, all right. And so I think that's all my announcements. And so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. So I'm gonna scroll up a little bit. And so this is from the notes last time, and so you don't have to write this down again. But I want to start with this result right here. And to kind of just remind you how we got here. And so this is kind of the integral representation of Fourier. Because up until this point, we've been covering the Fourier series, which is this guy right here, which is an infinite summation of discrete frequencies, right? So that was the main thing with the Fourier series, was that we had a summation, and we could only cover a discrete number of frequencies, which is an integer multiple of kind of the natural frequency of the system. Okay. And so kind of the motivation that we had with Fourier transforms is that we wanted to generalize this so that we can cover all frequencies. Okay. And so we went through the derivation, so I won't go through it. I won't go through the details of it again, but basically, we assume that we work under the assumption that we're working with a non-periodic function. And so we took the limit as the period went to infinity. Okay. And we ended up with this box result right here. So this result right here is known as the Fourier integral. Okay. And so it's basically the counterpart to our Fourier series. Sorry, I've had a sneeze lined up and it hasn't come out yet. Okay, it's one of those stubborn sneezes. Okay, so the Fourier integral, right? And so there's a lot of parallels with the Fourier series, right? And so, ignoring the A naught, ignoring the constant term, okay, you should see a lot of similarities. So this integral out in front right here, this is essentially the same thing as our summation in the Fourier series. Okay. But the reason it turned into an integral is because of kind of the assumptions that we made. And so we generalize it to an integral. Okay, so I want you to kind of draw that comparison. We have a cosine and a sine, and so that part is also the same. Okay. And so a Fourier series also has a cosine term, also has a sine term. And most notably, we have these two inner integrals right here. Okay. So the integral of f of t cosine of omega t, and then integral of f of t sine of omega t. Okay. These two things that I circle right here are basically our coefficients. Okay. And so this is like our an coefficient. And this one right here is our bn coefficient. Okay. And so before we move on, before we kind of talk a bit more about Fourier transform, I want to make sure that this parallel is kind of clear, because I know this was kind of the very last thing we did at the end of lecture last time, and so I want to make sure that you guys see the parallels, okay? Because we're going to start to work with this here. Okay, so that was just kind of a quick recap of last time, and so. I know we ended class last time with kind of a somewhat lengthy derivation, and I know when you kind of do those things, kind of the important message gets lost. You kind of lose the forest for the trees. So, I want to make sure we start from here and I kind of highlight kind of the important parts of this before we kind of move. All right, are there any questions on the Fourier integral here, or kind of anything that we did at the end of class on Tuesday? Okay. All right, so let's start from here. And so, what I want to highlight here is, or what I want to focus on first, are these expressions for our coefficients that I'll put in here. Okay. So let me move that down here. But we're still doing Fourier integral. So let's start. So let's start with writing our new formulas for the coefficients. So, in reality, they didn't change all that much. The only thing that really changed was that instead of, we don't have an n in there anymore, right? So instead of having integer multiple, we now have a continuous frequency function. So let's start with writing this. And so our first expression here, the one that's in front of the cosine term, is 1 over pi integral minus infinity to infinity of f of t cosine of omega t, okay. And our other expression was 1 over pi integral minus infinity to infinity f of t sine omega t e t. So again, these look very, very similar to our formulas for the coefficients in Fourier series with a few kind of subtle differences, right? Of course, the main thing is that L is no longer there, so we don't have any concept of period anymore with the integral, and there's no n either, right? So we've kind of lost our integer multiple, which is good. That was kind of our goal, right? And the other thing that you'll see here is the integration bounds go from minus infinity to infinity now. So these are now infinite integrals. But these terms here are very important. And so they kind of serve a very similar purpose in a Fourier integral. And so they're still going to be our coefficients, except now, they're not, those coefficients are not discrete values. These are now going to be functions of frequency, okay? And we're going to define them as such. And so this first integral here, I'm going to call it a function a of omega. And our second function here, I'll call another name b of omega. And so now, these expressions here are functions of frequency, a continuous function of frequency. And so, with these expressions here, we can write a more simplified version of our Fourier integral, one that's a lot easier to follow. Okay. So our Fourier integral is the following. So if f of t is equal to integral from 0 to infinity. That inner integral now is going to be replaced with a of omega sine t plus b of omega sine omega t d omega. All right, so these three formulas here are going to be key, at least for the first half of class. Okay. So we have our a of omega, b of omega, and then our Fourier integral down there. Okay. All right, so before we pause, I want to kind of highlight the difference between these two, and there's a reason I kind of put the two up top and then the one on the bottom. Okay. And so one way you can interpret these two formulas on the top is that essentially they're giving us functions of omega, right? And the integral that we're performing is over t. Okay? And so essentially, one way that you can interpret these top two formulas is we're basically making a transformation or a change of variables from time to frequency. So kind of squeeze something in there. So if you didn't leave that much from your notes, I apologize. But basically those top two formulas there are a transformation from the time domain to the frequency. Okay. In contrast, what we have down here, okay, one way that you can interpret the Fourier integral is that we have these two functions, a of omega and b of omega, okay. But the result of this on the left-hand side is a function of t. And so one way that you can interpret this as this is an inverse transformation. From the frequency domain back to the time domain. we're not quite there yet, so we're not quite at the Fourier transform yet. But this is going to be kind of the building blocks, and I kind of want to kind of incept the idea of a transformation in your head, just so that it kind of makes the rest of the class easier. Okay. Okay, so when you're dealing with these kind of transformations, it's always good to keep in mind what the end result of each transformation is. Right? So for the top two, our end result is going to be functions of frequency, so that's a transformation to the frequency domain. For the bottom one, the Fourier integral, our end result is a function of time, and so that's going to be an inverse transformation. Okay, any questions on this so far? Okay. All right, so let's do an example to kind of see how this how to actually use these. Okay, and so for this example, we want to find the Fourier integral representation of the following function. Okay. So we have f of t equal to, and we have a discontinuous function here. And so f of t is going to be equal to 1 if the absolute value of x is less than 1, and it's going to be 0 otherwise. So we have a non-periodic function here, and so we're not assuming this function is going to repeat. We just basically have a square pulse that's centered at the origin. Okay. And so visually it looks like this. Okay, so the horizontal axis here is t, the vertical axis is f of t, and so we just have a square pulse. The bounds are -1 and okay. And so we want to find the Fourier integral representation for this. And so in order to do that, we need to compute our functions a of omega and b of omega. So essentially we're computing the coefficients in quotes for the expansion. Okay, let's go ahead and compute that. So we have a of omega is equal to 1 over pi integral from minus infinity to infinity f of t cosine t. Okay. So that's our function for a. That's our formula for a of omega. And so let's go ahead and plug in for this formula here. Okay. So first thing I want to note here is that the function is going to be 0 everywhere outside of -1 to 1. Okay? And so we're going to split this up into 3 integrals. And so we're going to have an integral from minus infinity to -1 plus an integral. Well, let me write out the function though, just to make sure I understand this. And so from minus infinity to -1, based on the function that's given, we know that the function value is going to be 0. And so there's going to be an integral of 0 multiplied by kind of omega t. The next relevant interval for our function here is going to be from -1 to 1. It's going to have integral from -1 to 1. And the value of the function here is 1. So 1 times cosine omega t. Okay. And then our next relevant interval here is from 1 to infinity. So integral from 1 to infinity. And the function value in this interval is 0. So 0 times cosine omega t. Okay. All right. And so for the functions that involve 0, of course, we're going to cancel those out because integral of 0 is just 0. Okay. At least for a definite integral. interval 0, 0. If it was an indefinite interval, we'd have a arbitrary constant, but that's not the case. Okay, and so the integral that we are evaluating is integral from -1 to 1. 1 times cosine omega t is just cosine omega t. Okay. Let's go ahead and integrate this, and so we have 1 over omega sine omega t evaluated from -1 to 1. Okay. Oh, 1 over pi, forgot the pi. Okay, so we have 1 over pi omega sine of omega t and evaluated from -1 to 1. Okay. And so let's go ahead and evaluate this. And so we have 1 over pi omega sine omega minus sine minus omega. Okay. We know that sine is an odd function, and so when we have sine of minus omega here, okay, sine of minus omega here is just going to be minus sine of omega, right? So the minus sign just comes out in front. And so that minus sign is going to cancel out with the minus sign from the integration, and so we have sine of omega plus sine of omega. Okay. And so in the end, we can go ahead and write our value for our a omega. So a omega here is going to be 2 sine of omega divided by . So that's our first coefficient of our integral. But instead of being, discrete coefficients, we now have a function of omega. And so you see here that this result here, is a function of omega. So that's our new variable. All right. Any questions about how we got this result here? Okay. All right. So let's compute b of omega. All right, so formula for b of omega is 1 over pi, equal from minus infinity to infinity, f of t, sine t, t. So just like we did with a of omega, we're going to simplify this. And so, we know that from the interval minus infinity to -1, our function is just going to be 0. And so we don't need to integrate there. Same thing from 1 to infinity. And so for this particular function, it's going to be equal to pi integral -1 to 1 times sine t. Okay. And so to get that result, basically I split the integral just like we did for a of omega, and then just already cancel out the 0 parts. Okay. This right here we split. And okay, so let's go ahead and perform this integral. And so if we carry out that integration, we have 1 over pi omega times minus cosine omega t from -1 to 1. Okay. I'm going to go ahead and take that negative and let's bring it out in front. And so we have a minus 1 over pi omega. Okay. And then I'm going to evaluate this at the integration bound. So we have cosine of omega times 1. So that's going to be omega minus cosine of minus. So just like the previous part, we're going to take advantage of the fact that cosine is an even function. Okay, and so since cosine is an even function, cosine of minus omega is going to be just cosine of. We're just canceling out. We're canceling out that negative because cosine is the same on both, the right side and the left side of the vertical. Okay, and so if we plug that in here, we have cosine of omega minus cosine of omega, and of course that's just going to cancel out. So our result from this is d of omega 2. Okay. Right. So this part makes sense, right? So if we look at our original function, so the function that we started with in this problem, right? We have just a square pulse that's identical on both the left hand side and the right hand side of the vertical axis. And so our input function here, or our f of t, even though it's not periodic, we can say automatically that this is an even function. And so Fourier integrals, even though we have a different form from them, it still follows the same rules for Fourier series, right? So remember Fourier series, we had that kind of simplifying thing where if it's an even or odd function, we can already count some of the coefficients at 0. So here is the same thing. Okay? And so that's kind of another thing to kind of save you a bit of work when you're doing these kinds of problems, right? So before you do any Fourier problem, whether it be Fourier series, Fourier integral, look at the function and see, whether it's even or odd, and that's going to save you probably half your work. Because if it's an even function, you can already say, I'm not even going to bother. Bn's or b of omegas are going to be equal. Okay. And so now that we have a of omega and b of omega, let's write out our Fourier integral. And so our Fourier integral is f of t is equal to integral from 0 to infinity, a of omega sine omega t plus b of omega omega t d omega. Okay. Right, so that's our formula for the Fourier integral. And so we're just going to plug in for a of omega and b of omega here. Okay. So f of t is equal to integral from 0 to infinity. A of omega is 2 cosine omega, or it's going to be 2 sine omega over pi omega, and this is multiplied by cosine t. Okay. This is just here. Sorry, omega. And then our b omega here is just 0. And so I'm not even going to bother writing. So this is going to be integrated over. Okay. So that's our final result. And so, when you're doing these problems, I think most people would think, when you compute a of omega, b of omega, you think that you're done, but you need to go ahead and plug it back in because you need to actually write out the Fourier. All right, any questions on this example here? Question, Logan? Okay. All right, and so that's the basics of Fourier integrals. And so, I think from this example, and this is quite similar actually to a Fourier series. And so let's go ahead and move on to the next topic. Let's talk about how Fourier handles discontinuous functions. And so notice I didn't say Fourier series or Fourier integrals or Fourier transforms. This kind of goes for all of Fourier. Okay. And so the relationship between Fourier and discontinuous functions is something that's quite interesting, not only from engineering, but actually, from a math perspective as well. Okay. And so the way Fourier interacts with discontinuous functions, it does a few different things. And of course, when I say discontinuous functions, those are functions where the function value jumps suddenly from one to another at a particular moment in time. So actually, our last example was a good example of a discontinuous function. So if we draw out the last example again. And so our last example was this kind of square pulse right here. It doesn't really look discontinuous because I drew kind of vertical lines to kind of prevent that. But if you look at the function value at t is equal to 1, so at t is equal to 1, the function value jumps. And so it goes from a value of 1 down to a value of 0 very suddenly. So there's not really any smooth transition here. It's just kind of a sudden jump. So that's essentially what I mean by a discontinuous function. And the vertical lines here, I drew them just for kind of visualization's sake. But in reality, the function actually looks like this. Let me get rid of that. So in reality, the function actually looks like this right here. And so in reality, there's no vertical lines at all. And so it's just it goes from 0 up to 1 and then down to 0. Okay. Okay. And so when we have a function like this and we represent it with Fourier, essentially one kind of nice byproduct here is that it kind of smooths out the discontinuities. Okay. Okay. And so technically speaking, when you have a discontinuous function like this, the function value is actually undefined at the point of discontinuity. Okay? And so we can't really say what the function value is here at t is equal to 1, because it's both simultaneously 1 and simultaneously 0. But if you were to represent this function with Fourier, and more importantly, if you were to truncate that expression, so if you were to kind of only include a certain amount of frequencies, then you end up with kind of a smoother function. Okay? And so the exact property kind of goes like this. And so at a point of discontinuity, the value of the Fourier representation of the function. And again, this goes for both Fourier series and Fourier integrals, okay? And so the value of the Fourier representation of the function equals the average of the left and right hand limits. And so if you were to evaluate the value of a function at a point of discontinuity, all you have to do is just take the average of, what the value of the function was, the left of discontinuity and the value to the right. Okay. And so for this particular function here, okay, that means, if we were to use a Fourier integral representation or Fourier series, and we wanted to evaluate the function at t is equal to 1, we would get 1/2. Okay. So that's kind of a nice property. And so, when you have a Fourier representation, you don't have to worry about discontinuities because it kind of naturally kind of smooths those. Okay, any questions on this? Okay. All right, so that's one nice property about Fourier discontinuities. There's one not so nice property. Although I would argue that this property is actually really cool. It's just kind of, it's annoying, but it's kind of cool that it happens. Okay. And so before we talk about that, let's kind of talk about truncation a little bit, just because it's relevant here again. Okay. And so just like Fourier series, we can also truncate our Fourier integral representations. Okay. And so normally, our Fourier integral representation, we have an integral from 0 to infinity, right? A omega dot dot dot. Okay. I'm not going to write out the whole Fourier integral, but the main thing I want to highlight here is that our integration goes up to infinity. Remember, our Fourier integral is basically a transformation from frequency domain to time domain. And so by integrating to infinity, basically what we're saying is we want to include all frequencies from 0 to infinite frequency. Okay? So this upper bound, this includes all frequencies in our potential. Okay. So it's the same thing in Fourier series where we have kind of an infinite summation, right? So we go from n is equal to 1 to infinity. That's essentially the same thing. Okay. But just like in Fourier series, a lot of times it's not practical to integrate to infinity because we don't need all that. We don't need all that frequency information. Okay. And so we can also truncate this. And so instead of integrating to infinity, we're going to integrate to some fixed value. We'll call it A. where A is just some number. So, and the nice thing here is that A, we're not limited to an integer anymore. And so we can literally put any frequency here that would. And so this A, because essentially what we're doing, we're cutting off the frequency at A in our Fourier integral representation. This is often called the cutoff frequency. And of course, our Fourier integral representation is going to change depending on the cutoff frequency. Okay. All right. And so it's a little bit hard to kind of explain, how the function really changes. And so I think the best way to kind of show it is visually. Okay. And so I'm going to take our last example here, and I'm going to show you different plots of what the integral would look like for different values of the cutoff frequency. Okay. Okay. And so for all of these, I'm going to draw the original underlying function. And so remember, our original underlying function is our kind of our square pulse. And then on top of that, I'm going to draw the Fourier integral representation. Okay. And so our original function looks something like this. Okay, so I'm going to draw in dotted lines. And so let's start with a relatively low cutoff frequency. There's no units for this, but just 8. We're just going to use 8. 8 is a low number. Okay. Okay. And so for something like this, we would have a situation, that maybe looks like this. And so maybe we start high, go down here, up, cross right at the midpoint. That's pretty decent drawing. It's not bad for my standards. Okay. And so you can see we have this kind of oscillating kind of thing going on because of the sines and cosines, right? And so that stuff is always going to be there. But this is for a relatively low cutoff frequency. Okay. As we increase the cutoff frequency, what we'll see is that the function is going to do two things. And so it's going to hug, as we increase the cutoff frequency, it's going to hug our original function a lot closer. But it's also going to increase the frequency of the oscillations because we're including more frequencies in our response. Okay, so we have t, f of t. Let me go ahead and draw our original function here. Okay. And so let's increase the cutoff frequency. And so let's go up to 16. We'll have a is equal to 16. Okay, so for this one, maybe it looks something like this. We'll cross halfway through. And so, you can see this drawing maybe not as good. And so in this figure here, you can see we have more bumps, we have more oscillations because we have a higher frequency. But we're hugging our function a little bit better in general. And one thing you'll notice, in both of these representations, I made sure, when we had that discontinuity, when we had that vertical line, I made sure the Fourier kind of crosses right in between, so right in the middle of those two. Okay, so I'll draw one more because I have one more in the notes. So why not? We have T, F of T. Okay. And so let's do it for A is equal to 32. Arbitrarily high. Okay, so for this one, we're going to see kind of we're going to continue on that same trend. So we're going to have more oscillations here. We're midway through. Okay. And so it looks something like this. And so, again, you can see we continue on that same trend where, we're hugging the function generally a lot better, but the amount of bumps is getting more, which is not necessarily a bad thing. Having more bumps is not bad. It's just something to kind of be aware of. Okay, so let me kind of scroll up here so you can kind of see all of them together. Okay. All right, so hopefully from this image here, you can kind of see the effect of different truncation or different cutoff frequencies. Right? So as you increase the cutoff frequency, you're getting more and more accurate to the function. But there is one thing that is weird about this representation, and hopefully you picked up on it. Okay. And so no matter what we set our cutoff frequency to, we have these kind of almost like bunny ears on our result. Okay. So bunny ears, and bunny ears. Okay. So that's not a mistake. That's not my poor drawing skills at work. That actually does happen. And so you actually do have these, we call them overshoots in our function. Okay. And so these overshoots, they're known as what's known as the Gibbs phenomenon. Okay. And so that's something else. That's basically something else that Fourier does in the neighborhood of a discontinuity. Okay. And the very interesting thing about this is that, this phenomenon, this overshoot, actually does not get better when you increase A. And so you would think so, right? And so when you increase the cutoff frequency, generally what you expect is a more accurate representation. But this phenomenon here of the overshoots does not get better. It actually gets worse with increasing cutoff frequency. So the height of the overshoot gets worse, but as you increase the cutoff frequency, it kind of localizes it a lot more. So overall, it does get better, but the height of the overshoot gets worse. And so I don't want to kind of confuse it. So Overall, it does get better when you increase the cutoff frequency, but the overshoot itself does not get better. Okay. So this phenomenon is very interesting and very kind of cool phenomenon is known as the Gibbs phenomenon. Okay. So it's something that's interesting, and I think Gibbs phenomenon is something that people often forget when they're working with Fourier in practice. And so you would think Fourier has a lot of really nice properties, and we'll go over more on Tuesday at a time. So Fourier has a ton of really nice properties, and that's why it's kind of used a lot in industry or just in research or anything. But people kind of forget sometimes about the Gibbs phenomenon. So they'll represent their function with Fourier, and you'll look at your representation like, what the heck is this? Like, what's this? What the heck is this overshoot thing? Oh yes, it's the Gibbs phenomenon. So you can't really escape it. But at the same time, for a lot of practical functions, you don't have a lot of really hard discontinuities like this. You might have something that comes close to it, but in reality, if you're working with real data, you're not going to have sharp discontinuities. But it is something to kind of keep in mind as you use Fourier. Okay, any questions on this? Okay. All right, so that's kind of a nice aside. So that's kind of a nice side quest in terms of Fourier. Well, let's kind of get back on track in terms of Fourier integrals and Fourier transforms. Okay, so I know we already talked about it. We already talked about it in the example, but let's kind of formalize it. And so let's talk about simplifications you can make for even and odd functions. Okay. And so just like the last example showed you, if your original time domain function is even or odd, then you can simplify your expressions for A omega and B omega. And so let's go over each one individually. So for even functions, we already know that B of omega is equal to 0. Okay. But we can also simplify our formula for A of omega a little bit. Okay? Because normally our A of omega integral is from minus infinity to infinity. But if we know that the function is symmetric on the minus side and the plus side, then we only have to integrate for half. And so our A of omega is now going to be 2 over pi integral 0 to infinity. Okay. And so our lower bound here is no longer minus infinity, but it's now 0. Okay. F of t cosine omega t. And then for odd functions, we know that A of omega is going to be equal 0. So we don't even have to bother computing those. And our V of omega is simplified in kind of the same way. So we have 2 over pi, integral from 0 to infinity, f of t, sine omega t, d. So it's slightly easier. And so sometimes, when your integration bound is 0, that's often a lot easier than an integration bound of minus infinity. And so it's just kind of a nice trick that you can use just to simplify the okay. And of course, for even and odd functions, the other coefficient or the other function is just equal to 0. And so that's kind of a mistake. Okay, and so I wanted to make sure I gave you that because I think for homework 6, I think you do use this to kind of simplify your work. Okay. All right. So let's go ahead and now that we are we've kind of talked about the Fourier integral quite a bit, let's talk about now the Fourier transform. Okay. And so now, we're ready to kind of formally state, the actual transformation that we do to go from the time domain to the frequency domain. Okay. It's very similar. And so it almost feels a little bit cheeky to kind of actually, wait until now to define it as the Fourier transform. But it is slightly. Okay. And I will kind of make a comment that, if you remember back when we did Laplace, a big reason why we use Laplace was to basically transform differential equations into another form. Okay? You can do the same thing with Fourier transforms. And so you can use Fourier transforms in the exact same way that you use Laplace. And so you can use Fourier transforms to solve differential equations. It is possible, but it's also not very common. So, it's not something I want to really go over because it kind of takes away from all the other aspects of Fourier. Okay. But I did want to mention that it is possible. Okay. So let's go ahead and state the formal definitions. And so what you'll see here, there's various different flavors of Fourier transform. So we're going to start with the sine and cosine transform, and then probably on next Tuesday we'll go over the complex Fourier transform, and that one's kind of the more traditional Fourier transform. Okay. And so you'll see these look almost identical. The only thing is just that there's a different multiplier in front. Okay. And so we'll start with the Fourier cosine transform. And so I'll call it FC, F underscore C of omega. Okay. This is going to be square root 2 over pi integral 0 to infinity f of t cosine omega t. So you can see it's almost identical to our even function representation, except we just add a square root from it. Right? So it is a little bit kind of cheeky to call it something different, but this is the formal definition, and so we'll kind of stick with this. And then the Fourier sine transform is very simple. So f underscore s of omega 2 over pi integral from 0 to infinity f of t sine omega t. Okay, so what I've written down there right now, these are the forward transforms. So this is how you go from the time domain f of t into the frequency domain, big F of omega. Okay. But unlike Laplace, and so if you remember the way we use Laplace, the way we did the inverse transforms, we mostly use the table, right? And so we use the Fourier table. We just look things up in a table. For Fourier, we actually have a formula for it, and we actually use the formula more commonly than a table. Okay. And so on this side, I'll have the inverse. These are going to be the inverse transforms. Okay. We have one. We have one flavor for cosine and one flavor for sine as well. Okay, so for the inverse cosine transform, we have f of t is equal to square root 2 pi integral from 0 to infinity f underscore c of omega sine omega t d omega. Okay. And then for the sine version, that looks very similar. We have f t 2 square root 2 omega or 2 over pi, excuse me. Integral from 0 to infinity f underscore s of omega sine omega t d omega. Okay. So it's basically the same computations that we've been doing before, just that now they have a square root, so now they're more efficient. All right, any questions on this? Okay, all right, I got one more example today. I will save the complex Fourier transform for Tuesday because that's kind of its own thing. But let's do one example of this. Okay. And we're going to bring back an old friend. Well, it's an old friend for me, probably an old enemy for you. Okay. We're going to do an exponential sinusoid integral. Okay, so we'll do that one together. All right, so let's find the cosine Fourier transform f of t is equal to e to the minus t. Okay. We have a decaying exponential function. Okay, so let's go ahead and plug in. And so we have our formula for the cosine Fourier transform here. Fc omega 2 square root 2 pi integral from 0 to infinity e to the minus t cosine omega t e. We can't escape this integral. This integral keeps coming up, and no matter what unit that we're in. Differential equations, Laplace transforms, calculus, Fourier, can't escape it. It always comes. Okay, but we'll do this one together just because we have time in class. I think we had one of this last time, but but we didn't have time last time, so let's do this one. All right, so let's go ahead and integrate this by parts. And in fact, I'm going to use my favorite kind of shorthand technique. So I'm going to integrate this by table. And so the way I like to integrate these things is I like to make kind of a table like this. And so on one side we have u, and so that's going to be the part of the integral that we're going to differentiate. And then for the other part dv, that's the part we're going to take the antiderivative stuff. Okay. And so you can actually choose whichever one you want. And so, for most people, I think they would choose e to the minus t as your u, and then your cosine as the dv. But I'll show you that if you actually swap them, you actually get the same result. And so let me put cosine omega t. Okay. We're going to put cosine omega t on the u part here. And then we're going to have e to the minus t the dv. And so on the left side of this table, we're going to take derivatives, and on the right side, we're going to take anti-derivatives. Okay, so derivative cosine omega t is going to be minus omega sine omega t. Let's take one more derivative, and so we have a minus squared sine omega t. Okay. So take derivatives. And then on the other side, we're going to take antiderivatives. Okay. So antiderivative of e to the minus t is just going to be minus e to the minus t. We take another antiderivative, that negative is just going to cancel out. So we end up with e to the minus t. Okay. And so I chose it this way just because I knew that if we took the antiderivatives of cosine omega t, we get a fraction, so 1 over omega. And you know, at least for me personally, I don't like to deal with fractions, and so you know, okay. And so now that we do, now that we have this table set up, we are now ready to kind of cross over the rows. Okay. And so generally speaking, remember when we do integration by table, we put the rows, or we put our arrows going diagonally down to the right. Okay. And so we're going to have cosine omega t, that's going to be linked up with e to the minus e to the minus t. And then minus omega sine omega t is going to be linked with e to the minus t. Okay. And remember, you know, when we draw these arrows, that means we're going to be multiplying those two terms. Okay. And the sign that we're going to choose for this is going to alternate between positive and negative. So positive here, negative here. Okay. And then when we reach the bottom, you know, we're going to go across horizontally, right? And so instead of going diagonally down, we're going to go horizontally. Oh. And so this horizontal multiplication means that we have to keep it in an integral, okay? And so we can't pull it out like the other. But we're still going to keep our same sign convention. And so we're going to have a positive there. Okay? So plus minus plus. Okay. So now that we have this table set up, we are now ready to you know, solve for the integration. I'm gonna ignore the square root 2 over pi for now, just because it's just a constant term. Let's focus on just the integral. Okay. But we'll bring the square root of 2 over pi back. Okay. And so for this we have integral 0 to infinity e to the minus t sine t dt. Okay. So that's the original integral that we want to solve. And then now on the right hand side of this equal sign, we're going to put the results of our. Okay. Okay. So first term that we have cosine omega t. Cosine omega t multiplied by e minus e to the minus t with a plus sign. Okay. So that's going to be minus e to the minus t sine t. Then we have a second diagonal multiplication. And so this is going to be a minus minus, so that's going to be plus omega e to the minus t sine omega t. And finally, we have the last bit here, which we're going to keep in an integral because it's a horizontal multiplication. Okay. So we have plus but then we have a minus that comes from the cosine. So we have a minus theta squared integral 0 to infinity e minus t cosine negative t. Okay. It's a lot of terms, a lot of exponentials, a lot of cosines, but just about there. All right, any questions on how I did this integration by table here? If you're more comfortable doing just more classic integration by parts, then by all means go for it. But I personally like this method just because it just saves a little bit of time, a little bit of writing. And once you get good at it, it becomes kind of almost this kind of second nature. Okay. But basically this integration by table, I think like I've mentioned before, is just integration by parts twice. Okay. And you can even continue this on if you even want to, but this is kind of where we need to stop for. Okay. All right, and so at this point, one thing you should notice, and the reason I kind of stopped the table here, is that what we need to solve for is this integral right here. So integral from 0 to infinity, e to the minus t cosine omega t. Okay. And then out of our integration by parts, you should see that we got the exact same thing. So we still got this integral from 0 to infinity, e to the minus t cosine omega t. So what I'm going to do is I'm going to move this over to the other side of the equation. Okay. With that omega squared in front, okay, so we're going to have 1 plus omega squared integral from 0 to infinity, e to the minus t is equal to minus e to the minus t cosine omega t plus omega e to the minus p sine omega t. Okay. So now it becomes an algebra problem because now we have an explicit expression for our integral here. We just have to divide by that 1 plus omega squared. Okay. So let's go ahead and divide by this. So we have integral 0 to infinity e to the minus t cosine t minus e to the minus t cosine t plus omega e to the minus t sine omega t over 1. Okay. And so now we're going to evaluate this. And so we've essentially performed the integral here. And so we're going to evaluate this at the integration bounds from 0 to infinity. Okay, and remember we're plugging in for t because that's our integration variable here. Okay, so let's go ahead and apply these integration bounds. And so right away we can see that we have e to the minus t in our result. When we apply this at t is equal to infinity, when we apply this at t is equal to infinity, this is going to go to 0 because e to the minus infinity is just 0. It's not just 0, it's omega 0. And so, we can go ahead and cancel those terms out. Okay. Okay. And so the result of this integration is we're going to have a bunch of terms in here. Or this is going to be our terms evaluated at t is equal to minus infinity. Okay. Or t is equal to infinity, excuse me. Okay. And so all those terms, when t is equal to infinity, because we have that e to the minus t multiplied by each term in our expression here, this is just going to be equal to 0. So I'm not even going to bother. Okay, and so that leaves us with the other terms. And so we have e, and so now we're evaluating it at t is equal to 0. So e to the 0 cosine of 0 plus omega e to the 0 sine of 0 divided by 1 plus omega. Okay. So it's 9:45, but I'm going to go ahead and kind of just skip to the result. We're basically there. And so sine of 0, we know is just going to be 0. Cosine of 0 is 0. Both our e to the 0s are just going to be 1. Okay. And so this tells us that our cosine transform fc of omega equal to 1 over 1 plus omega squared. So there should be a negative here. And then we can't forget our square root 2 or pi over 2, 2 or pi. Okay. Remember, that was the constant that was in front of our integral that I said, for now we would ignore it, but we bring it back in. So, if you are going to do that, just to simplify your integration, just don't forget about the constants. Bring them back in. All right, any questions on this example here? Yeah.
Can cosine of 0 be 1?
It is 1, yes. Thinking ahead of us. Okay, thanks for catching that. Yeah, otherwise this whole thing would be 0, and that would be a big waste of time just to do all this work and get 0, right? Question? No. Oh, okay. Okay, all right, so that's all I got for today. And so I'll see you guys back on Tuesday. We'll finish up the rest of the Fourier transform notes. And then that'll be the cutoff for the midterm. So I think we have about half a lecture left to go for Fourier, and then we'll be done with that. And then we'll move on to probability and statistics. So thank you guys for coming today. As always, appreciate you guys being here, especially so early in the morning. Hope you guys enjoy the rest of your day. Hope you guys have a good weekend, and I will see you next week.
Oh, bro. You're gonna point them.
And Jason, any final questions? Okay, all right, so I'll see you next week.